Today we're covering Chapter 3, Ecological Threats, and as always I'm going to repeat the advice that please read the textbook completely, thoroughly, at least once, take notes, maybe reread again. Today's lecture, this is what we're covering, or most of these topics, but as always, the narrated PowerPoint isn't 100% complete. It's just kind of an addendum to reading the textbook. It can help out flesh out some parts, and we also do skip over some parts because we don't want to make a very long PowerPoint audio that no one will listen to. So you can see the definitions listed out before you, and I always think it's a little bit funny or ironic that we even have to define what an ecosystem is, as it was the only system, the only reality on planet Earth until very recently. Now, of course, we spend time, most of our time, and we live in more human-made environments. Today we're discussing how the broader ecosystems of planet Earth both house and interact with our food systems. How do our food systems fit into the ecosystem? How do they impact the ecosystem? And how do our food systems benefit from the ecosystem and at times also harm the ecosystem? The graphic on this slide is both symbolic and literal. We have humans, for the most part, living apart from unspoiled, or you could say less spoiled, natural ecosystems. So here in the graphic, literally the river flows downstream to the city where people use the water for bathing, for drinking, for washing, for a million different things, right? The water is an example of an ecosystem service. That's something that the ecosystem provides. We'll discuss many more examples shortly. Ecosystem services is a crucial concept and one that few people understand. Our ecosystems are often underappreciated and overexploited. We divide ecosystem services into 4 categories. You can see those in the top right graphic. On this slide, we're discussing in brief provisioning. So you have a few obvious examples on the slide, and to be more specific, things like animal protein, beef, chicken, often the skin of animals like the leather off of the skin of cows, or animal furs, really every part of the animal. Bones are often used for fertilizer. Some organ meat is often used for domestic animal feed, like for dog food. We take stones from building out of nature. Natural rubber comes from rubber trees. There's also synthetic rubber, but that doesn't work for every application. Paper coming from timber, some medicines coming directly from nature. We are getting more out of the ecosystems that we have than ever before. Consider the booming yields of agriculture. Corn and soy are great examples. Those advances that allowed for greater production came with machinery, advanced breeding of crops and animals, use of agrochemicals. All those we'll cover in a later chapter. Another specific example of provisioning is pollinating. So farmers actually pay beekeepers to come and supplement wild bee populations. So beekeepers come to different farmers' fields and unleash large quantities of bees, and those bees run around the farm, fly around the farm, and pollinate the crops, transfer pollen between plants, which greatly increases productivity. So the ecosystem provides some pollinators, provides some bees, also wasps, bats, lizards. There are quite a few other different kinds of pollinators out there. But wild pollinator populations are in decline over the recent decades. Um, Thought might be connected to uh, toxins in the environment, certain pesticides, certain herbicides, um, lots of different studies going on about that. But bee pollination adds $15 billion to our farm productivity. So it greatly increases productivity of food crops and is a good example of an ecosystem service, albeit often supplemented by humans who are keeping pollinator populations domestically. Another one of the four ecosystem services is regulating. So you can think of something as simple as that big tree that shades your house or apartment building. That can make a huge temperature difference and can really reduce the need for air conditioning in the summer. That's a very kind of minor example. Another example is climate. So having a healthy ecosystem reduces the risks of flooding, costs to coastal areas, losses to farmers from extreme weathers, droughts, floods. Trees and foliage more broadly trap some air pollutants, makes the air cleaner, lowers healthcare costs, and just to go into a little bit more detail on the water purification part, wetlands specifically purify water by removing pollutants and excess nutrients and by converting some of them into less harmful forms. Wetlands also protect against flooding, and this has been a major issue in many coastal areas of the U.S., most famously in New Orleans, where there's been a lot of loss of wetlands around New Orleans, and also barrier islands, which are another ecosystem. And overall in the U.S., we've lost about half of our wetlands in relatively short time. On page 62 of the book, that issue is discussed in a little bit more detail. This ecosystem service is a little bit more ethereal, the cultural benefits that ecosystems offer. So if you think of any activity in nature, hiking, walking, swimming on the beach, mountain biking, provides a very strong psychological boost to humans. We evolved in nature, and we need that connection to nature. That is our original ecological niche. If you think to yourself, if any of you ever done a guided meditation, I taught a stress management class at one point. I had students write their own guided meditation. I didn't give them any specific instructions. I just said, write a guided meditation that makes you feel relaxed. Every single person picked a nature-based guided meditation. Walking in the forest, watching clouds in the mountains, floating down the stream, watching the stars at night. Nobody picked a urban-based or human-made ecosystem as the focal point of their meditation. The supporting ecosystem services are the ones that maintain the fundamental ecosystem processes. So providing habitat for plants and wildlife, the maintenance of genetic and biological diversity they'll provide for the long-term vitality of the ecosystems. One example would be the photosynthesis that essentially creates everything ecosystems are built off of. photosynthesis, of course, combines water and carbon dioxide driven by the energy of sunlight. This creates all the natural material, the base of the ecosystem, all the plant growth that feeds all the animals and the other plants. If you're paying attention to the news, you will see something related to this topic on a weekly basis. For instance, some of the rise in food costs is due to climate change. Some sensitive crops, such as chocolate and olive oil, for instance, are among the ones to be affected the most. I'll say in Nicaragua, where I did quite a bit of research, there used to be 2 pretty reliable harvests a year for many important crops. Now it is more like 1 a year. And I talked to many farmers there who said because farming is becoming more unpredictable over the past few decades, a lot of farmers are tempted to leave the profession. And as more farmers leave the profession, that further endangers the food system. And you might think, well, this won't impact the U.S. It does, because we do import quite a bit of food, so it does impact us. The ecological footprint is a metric for consumption of resources. So it measures how fast or how much we consume resources and generate waste compared to how fast or how much nature can absorb our waste and generate the replacement resources. There is an activity around this as part of the course, so I won't go into too much detail because you'll learn more by doing the activity. Just to mention briefly, though, the American average is about 7.19 global hectares. That's about 17.7 acres. And you can see here where the USA fits in. We're up there very close to the top of countries in terms of the biggest ecological footprints. And you can also, of course, see a strong correlation here with income. And a football field, by the way, American football field, 100-yard field, that's about 1.3 acres. So a typical American needs about 14 football fields of land to support their lifestyle. You'll find out what you need when you do the exercise on the D2L site. The global average is about 1.8 hectares, which is about 3.5 football fields. So considerably lower than the American average. The 10 elements of agroecology. So an example of some of these at play is bringing back an older style of agriculture before specialization led the farmers focusing on either raising animals or plants, and often just a few species of one of those options or even just one. So prior to the 20th century, almost all farmers had many species of plants and animals that they were raising, and they were practicing agroecology for the most part. And now many farmers are going back to that. So bringing back different species of animals and plants on the same farm and working with some of the synergies that are possible. For instance, pigs eating human food that's no longer fit for human consumption. So old bread or cheese that has fungus on it, or pigs will eat almost anything. So you can feed pigs that food that would otherwise go to waste. And those pigs then create manure for the farm, which increases productivity. And of course, eventually, those pigs get up to weight and they're slaughtered for meat and bring in income to the farm. Some of the other elements of agroecology here The chapter does a good job of covering this. Please make sure you read Perspective 3.1 on page 70 of your book for a great example of sustainable farming. That will cover most of these elements well. This graphic shows the ideal of a food system that is able to be productive while balancing economic, environmental, and social needs. So still there's sufficient income, and at the same time the environmental services are valued, the water is drawn at a sustainable rate, the soil is replenished, and there's also a social element that values health, tradition, culture. So we'll go into detail on more of the ecosystem services broken down by soil, freshwater, oceans, and biodiversity. And us humans are very unique from other animals. If you think we're the Arizona Wildcats at University of Arizona, why aren't we the polar bears? Well, of course, polar bears can't thrive in the desert, right? What happens if you move a polar bear to Arizona? It won't last long. Human beings are really unique because we developed the cognitive niche in ecology, meaning we developed our brains to the point where we could alter our environment and thrive in almost any environment. Other animals adapt to the environment. Humans can adapt the environment to us. So if we think of this generally, there's a wide range of quality of soil. Soil can be full of microbes, rich with organic material, and be very productive for food production, or it can be very poor quality soil. Parts of the ocean can be uncontaminated and full of marine life. Other parts of the ocean are dead zones because of human activity. When we talk about farming and we specifically talk about soil fertility, it's good to mention that human beings are about 200,000, 300,000, 400,000 years old, depending on which anthropologist definition you take of Homo sapiens. The farming only started about 10,000 years ago. And even 10,000 years ago, it was only in certain areas and pretty niche. It became much more widespread in the past 1,000 years, and past 500 years really became the dominant form of human activity on Earth. So we're still learning this. We're kind of still learning how to be good farmers and good food producers. Just as early Homo sapiens took tens of thousands of years to learn how to be good hunter-gatherers, right? The best soils are deep. They go down many feet of organic material. They're well drained and have a neutral pH. We pull nutrients out of the soil into food, but we don't always replenish soils. We're still learning how to do this. This topic in general of the U.S. food system and food production is so much more important today than it once was, because simply our world population is massive today. Hunter-gatherers had very few children because of the constraints of that lifestyle. A lot of movement, a lot of traveling with animal migrations, traveling with the seasons, no permanent settlements. It's very difficult to have more than two kids. So if you go back to when agriculture was first being developed about 10,000 years ago, there were only about 5 million people on the planet. Unbelievable to think that. The average state in the U.S. has more than that, right? A lot of cities have more than 5 million people. And the population stayed fairly stable, and as we got better and better at farming and some advances as well in public health and medicine, the population didn't really take off until very, very recently. You see the Black Death there, that little dip, that's in the 15th century. So it started going slowly, slowly up, and then really started climbing with industrialization and more mechanized farming, more advanced medicine in the 19th and 20th century, more specifically. There is a lot to take in on this timeline, so I'll let this sit here for a minute. But one question students often have is, why didn't population boom as soon as agriculture started? And it goes back to that concept that agriculture is quite complex, and we didn't become experts at agriculture till fairly recently. And as you're learning in this chapter, there's still a lot of obstacles to make agriculture work smoothly long term. Agriculture, was very, very primitive at first. A lot of feast and famine. The Bible talks about this. 7 years of plenty followed by 7 years of famine, right? There wasn't much understanding of soil health for thousands of years, of flood mitigation, and also other aspects like how to store food without it spoiling. So the Green Revolution, which happened in the 20th century, which was a big revolution in plant hybridization that went along with the Industrial Revolution of kind of a fossil fuel powered farm economy. That, along with big reductions in child mortality, death in childbirth, big reductions in infectious disease, ability to purify water, other things that came along with the scientific revolution. That combination of factors is what caused population to really boom. This slide shows the causes of soil degradation. You can look at the color coding: deforestation, overexploitation for fuel wood, overgrazing, agricultural activities, and industrialization. We'll go into a couple of these in coming slides here. So many of the modern farming techniques, they can increase production in the short to kind of mid-term, but often at the long-term cost of soil and ecosystem health. This happens both with raising plants and animals. So with raising animals, it's often something like overgrazing natural areas to raise cows, sheep, goats. The animals gain weight quicker, there's increased profits, but they're consuming the plant matter of the land quicker than the land can produce it, which causes the ecosystem health of the land to go downhill over time. And I'll go into a couple specific examples here in a minute. How do we help the soil fertility? So, for instance, cover crops. Those are crops that are plowed or pulled like weeds after being grown or mulched. They aren't harvested. They're crops that build soil health. Livestock that can provide manure for crops. And probably in the future there's going to be more innovation. For instance, there's a lot of research now into little robotic droid kind of things that cruise over the soil to kill weeds, so you don't have to use as much pesticides and herbicides and fungicides. So what does good soil look like? You see an example there, and that YouTube video that provides a good 1 minute link into how good soil and poor soil differ. But one of the characteristics of good soil is that when there is rain and downpours, the water will seep deep into the ground versus pooling at the surface. Some of the techniques that build good soil we mentioned before, but things like crop rotation, no-till agriculture, which is doing agriculture without tilling up the land with big machines, composting, so putting nutrients back in the land, use of cover crops, and letting land fallow, which means giving parts of the farm a rest. So no plant or animal use for a year to let the land regenerate. Letting land fallow, that practice actually is mentioned in the Bible quite a bit. It's an old practice. Soil is formed through the process of rock weathering. So weathering is the breakdown of rocks into smaller and smaller particles. This happens through contact with water, air, or living organisms. So it can occur physically, biologically, or chemically. Lichens are often, they use rocks as their substrate. So they break down the rocks and create new soil. Lichens are a complex life form that has a symbiotic partnership of two separate organisms, a fungus and algae. So that's along with water and air. Those are the main ways that soil is formed. And it takes a long time. So again, we don't want to use up the soil at a rate faster than nature can create it. So I threw this picture in to show that this is even a fairly small tractor, and it's still about 10 to 20,000 pounds, and that impacts the land. It literally compacts the land. So you have this great weight pressing upon it, and that makes it more susceptible to erosion because there are no roots to hold it in place. And you also notice that another downside of mechanized farming is look at how much space there is between the rows. So that is just compacted soil that has no cover on it, that's susceptible to erosion. And so the farm is kind of more space than it is productive land in a way. Of course, that's not the same for all crops, but this is an example. I want to flesh out some of these concepts with a specific example from when I was working in Nicaragua. I spent a lot of time there in northern Nicaragua doing nutrition studies in pretty impoverished communities, and I learned about the history of the land because it was very related to the project I was working on, to health in general, to economics. And I remember the first time I got to this area, I thought, oh, how beautiful. It kind of reminds me of Northern California, these rolling hills. And I later learned that that land was all covered with forests, and it had some small farms and gardens intertwined in between the forests. But what happened is post-World War II, in the late 40s and 50s, the government wanted to raise more money so they could industrialize the country, and so they turned these small subsistence farms into much larger farms and to monocrops. And one of the things they did was turned a lot of this area into cotton farming. And at first this made a fair amount of money and helped the country industrialize, but the yields dropped after a few decades. The land wasn't ideally suited for cotton farming, and the nutrients were being pulled out of the soil quicker than they could be replaced. And then when it was no longer suitable for cotton farming, they turned it to cattle grazing. But the rainfall was decreased. Forests attract rainfall, and without the forest, the rainfall decreased. And the cattle overgrazed the land. There was too much economic pressure to produce too much meat and dairy too quickly. Again, a fair amount of money was made in the short term, but the land kept getting worse and worse. And now a lot of, especially the steeper areas of northern Nicaragua, are not particularly biologically productive because they are kind of shallow soils, nutrient poor, and fairly eroded as well. So, especially on the steeper slopes, when these were forested, the soils were in very good health, and the roots of the trees and the underbrush went down very deep. And when there was rainfall, um, the soil was able to hold that water content, and it went pretty deep. And it also evaporated back up, which the trees caught part of that. As there was more and more deforestation, the soils were of more poor quality and more eroded, and more of the water ran off. So it didn't stay in the ecosystem, it went downstream. So back in the USA here, another big threat to food production is urbanization. So this is, or suburbanization. So much of this has happened in areas perfectly suited for farmland. For instance, all along the East Coast in some of our most populated areas, Maryland, New Jersey, Connecticut, Pennsylvania. As cities spread outward, farmers sell their land to developers, subdivide it, and build houses on it. Um, the cement doesn't hold water. You get a lot more water runoff. Obviously, the soil quality is going downhill. This happens all over. Also happened a lot in Northern California, which is really ideal for agriculture, but became very valuable land as population increased. There are some legal efforts to preserve farmland, and that's happened in various parts of the country. So there's positive news there. So there are efforts all around the country to prevent farmland conversion, and one of these comes from Montgomery County, which is a county right outside of Washington, D.C., which is where I grew up, so I'm really familiar with that area. Montgomery County was prime farmland for centuries, and as Washington, D.C. became a more populous region, there was a lot of pressure on converting that farmland to suburban subdivisions. But there was also the knowledge that we need to keep some of that farmland. So there was some activist movements that worked through government regulation to preserve quite a bit of the farmland in Montgomery County, and it's really improved the quality of life there. So these rural areas are popular. People go biking, they go hiking, they do farm tours. There are wineries there, and those farms provide a lot of fresh food to the Washington, D.C. area, and also help with things like clean air, clean water, wildlife. There are also hunting, fishing, and boating activities there. So in that region, there's a good balance has been able to be found between the competing interests. Anytime you talk about agriculture, you're also talking about water, and of course fresh water, because you can't grow crops with salt water. Well, unless you have desalination plants, which there are around the world, but those require a lot of energy to run. So here in the US, when we're talking about fresh water, like the rest of the world, we're using most of our water in agriculture. And we do a lot of growing out west, including here in Arizona. And with the settlement patterns in the U.S., which were predominantly east to west, right? The East Coast got settled earlier. There's a lot more water back east, and there's very good soils and good agriculture, but a lot of that land has been taken up by human settlements, right? So out west, when the Hoover and Glen Canyon dams were built back in the earlier part of the 20th century, very few people lived in the Southwest. There was a lot of potential for agriculture, um, but there weren't people competing for that water supply. So more and more people have moved into the Southwest, and it's almost, in parts approaching, like in Southern California, an East Coast style population density. So you have more competition for the same water resources. So talking about scarce water resources, anyone has seen this image before? A lot of times students in my class, students from this part of the country, will recognize this image. So this is the San Juan River, which connects to Lake Powell, and the image with more water is from 1999, and the image with less water is from 2015. So there's been more and more demands on water sources in the Southwest, to the point where governments are now talking about maybe making a desalination plant in the Sea of Cortez in Mexico and pumping that water from across the border into Arizona, because our demands for water are outstripping resources. This is an example of one of the issues you have when water demands outstrip supply. So earth fissures occur in areas of extensive ground subsidence, which is when so much groundwater has been withdrawn, the ground subsides unevenly, can create stress along basin margins, which leads to earth fissure formation or ground fissure formation. Counties in Arizona host a lot of earth fissures, including La Paz, Maricopa, Pima, Pinal County. Pretty common sight in Arizona. So these figures are averages, of course, because the amount of water it takes to raise different kinds of food is going to vary greatly on the geography. So some areas have a lot of what's called green water, which is essentially rainwater, water that is in the soil, in the first couple feet of the soil. It doesn't require human intervention to get to. Blue water is water from rivers, reservoirs, aquifers that's used for irrigation, so that requires some human intervention to get to, right? And we can also overuse those kinds of resources. The typical vegetarian uses a lot less water to raise their food than a meat eater, and that's just because of the simple fact that if you're eating meat, those animals have to get to weight, right? So for a chicken, it might only be a few months to get to weight, but during that time, the chicken is consuming water and food that was raised using water. A cow might take quite a bit longer, a couple of years to get to weight before slaughter. It's eating a lot of food that required a lot of water to raise, and it's also, of course, drinking water. So that is why any animal food is going to have a lot higher water requirements to raise than fruits and vegetables and grains and legumes, any non-animal food. In an agroecology approach to farming, there is more emphasis on how to both use less freshwater resources and also how to protect our water resources. So as you can see in the photo on the bottom right, you have an area that's farmland, but you have what's called a riparian zone between the farms, which has a buffer space of natural vegetation, a lot of trees and bushes and foliage, and that protects the water quality of the creek. There's a creek flowing through there, so if we took that same picture in wintertime, you could probably see the creek flowing through, but this picture is in the summertime, so it's very green and you're not able to see the creek below the greenery. So it's not just about protecting creeks and rivers, it's also about protecting wetlands. And wetlands are marshy areas where water remains close to the surface. And some wetlands are seasonal in nature, and some wetlands are year round. We've lost a great deal of our wetlands over the past 70 years, about half of our wetlands. Around the 70s, they started to be movements to protect wetlands, and there have been more environmental laws put in place since then, and that has slowed the loss of wetlands. Continuing with the theme of water, we'll talk a little bit about oceans and about the animal protein we consume from the ocean, so fish and seafood, although we also consume seaweed, so it's another food product that we get from oceans. Globally, there's a great deal of overexploitation going on, which means that we're fishing at a rate that the natural stocks of fish can't be replenished, and so that the trend over time is that fish harvests and seafood harvests are smaller and smaller. So one of the ways we can make up for decreasing yields of animal protein from our oceans is by doing aquaculture, raising fish and seafood, kind of like we raise domesticated animals on land. So a little bit like raising cows or chickens. So we have a controlled environment. We have the fish or seafood in a penned in the area. Sometimes it's on the banks of a river. Sometimes it's in the ocean, but there's like a mesh lining that keeps the domesticated seafood from the wild populations. And oftentimes it's done in big man-made ponds. I spent about a week in such a place in Nicaragua some years ago. Very interesting experience. There they were doing farm-raised shrimp in man-made ponds, and they were feeding the shrimp mostly little plant-based pellets, flakes. I think it was mostly soy and corn. It's a long time ago though, so I'm not quite sure. But some of the issues with that is when you have animals in close contact with each other, just like with domesticated animals, infectious disease can rise, and then you're putting antibiotics in the water to reduce the transmission of or the treatment of the infectious disease, and you also get a lot of waste material building up. So there are some environmental issues, but when done right, aquaculture can be a really effective way to replace some of the protein loss from over exploiting natural stocks of fish and seafood. This dead zone south of Louisiana has come up a couple times in this class, and it will really come up in most classes on agriculture or water quality. The Mississippi River is the largest watershed in the U.S., and a watershed is the area drained by a river and its tributaries. And it's the fourth largest in the world. So the Mississippi River drains an area of about 3 million square kilometers or 1 million square miles, which is all or parts of about more than half the states in the U.S. and even a couple Canadian provinces. So each year, a lot of sediment comes from runoff from farms in the Midwest. That sediment has agricultural inputs like nitrogen and phosphorus in the sediment. It also has some pesticides, herbicides, fungicides, other agricultural inputs in it. And that flows down through the end of the Mississippi River and dumps out there in the Gulf of Mexico and creates this massive dead zone. The dead zone is caused by a process called eutrophication. So that's the high nutrient levels that are coming off, and also agricultural chemicals and sediment that are coming out of the Mississippi River, and that supports a lot of algae growth. And the algae, the bacteria that feed on this algae consume oxygen. Then you get areas of very low oxygen levels. You also get reduced sunlight from all this material at the top layer of the ocean. And so that threatens the survival of all sorts of aquatic life. So how we conduct agriculture has a really massive impact. And this is probably the most dramatic example in the U.S., but on a smaller scale, this happens at the mouth of many watersheds. So how can we avoid more dead zones like we have off the coast of Louisiana? Going back to some of the principles of agroecology, which we discussed earlier. So if there's no synthetic fertilizer use, there's much less runoff of anything problematic going into the natural watershed. Also no synthetic pesticides. How can you replace those? You can do integrated pest management, so you bring in ladybugs to eat different pests. You mix up the crops more so that one pest can't thrive in a monoculture environment. You do more green manure, like the cover crops, and composting. You do the buffer zones, long riparian zones, which we discussed earlier. And there's actually a lot of innovation too in terms of ways to replace synthetic fertilizer. So things like worm castings, fly castings, all sorts of new techniques are being developed. The biodiversity issue in agriculture works on two levels. One is that agriculture itself can cause substantial loss, right? Logging forests or draining wetlands to convert into farmland, right? And the other issue is the diversity of the food crops themselves. So as our agricultural system industrialized, we went from a very wide variety of different fruits, vegetables, grains, legumes, and actually farm animals themselves to a much narrower group of food products, because that was a little bit easier to do to scale. A certain kind of tomato that produces tomatoes that are easy to harvest by machine, that are a bit more durable, kind of chicken that can gain weight quick and be resistant to disease when put in small enclosures. So for instance, who buys the most potatoes in the USA? McDonald's. And McDonald's wants consistent flavor in all of their fries, and the machinery is calibrated to a certain potato, moisture level, texture, etc. So we've gone from a very wide variety of types of food to a much smaller variety. So we've lost quite a bit of diversity in that respect. This slide sums up some of the techniques of agroecology and how it impacts, benefits biodiversity. And we've gone over most of this in the textbook, goes into a lot of detail, and some of this I know might sound very kind of do-gooderish, but it actually also often works out financially. I mean, for instance, the loss of bees has cost hundreds of millions of dollars. Farmers are now paying more and more beekeepers to pollinate crops because the wild populations of bees are decreasing, and they're decreasing because of agricultural techniques that aren't favorable to nature. And pesticide inputs, all these agricultural inputs such as pesticides, fungicides, herbicides, they're also quite expensive. So It's getting to the point where, on some levels, the organic and sustainable agriculture is beginning to be able to compete with conventional. Also, charges more because it produces often a better, tastier product. So, just a few more last points on agroecology. We talked about organic farming some, but to sum up, a farming system that tries to minimize the use of synthetic pesticides and fertilizers, emphasizes soil quality. It is a legal definition, so to be certified organic, you need regular visits from the USDA to make sure that you're following the organic rules. And there is a certain small group of limited agricultural inputs, certain kinds of milder pesticides that degrade quicker that are allowed under certain circumstances on organic. So the legal definition of organic isn't quite 100% pure. It's a little bit of a compromise. Organic agriculture often utilizes these other techniques of agroecology, so crop rotations, which is 1 year a field is for wheat, the next year it's for maybe a legume like beans that would put some nitrogen back in the soil, and that mixing of the crops can help keep soil healthy. Green manure, so that's legumes that fix nitrogen. Agrovoltaics, actually the book doesn't mention this, but I want to throw this in there. It's a relatively new field, so that's the combining of producing solar energy on the same land where you are harvesting crops. So you can see if you put the solar panels up, about 10 feet high or so, you can do a lot of harvesting under those solar panels. So there's a lot of research going on about this, and there are certain crops that do really well with the additional shade from the solar panels. Of course, there's some crops that are going to be not as effective. They need a great deal of sunshine, and depending on the climate, location, the season. But there are a lot of applications where solar panels can really be a win-win in agriculture. And the last point, agroforestry, which is cultivating tree species with food production. So certain species of trees where you're grazing cattle, or where maybe you have free-range chickens out there, or different crops. Alright, that's it for chapter 3. As usual, make sure you're reading the book. The PowerPoints are not substitutes for the book. And always get back to me with any questions and answers. And if you have questions that you think other folks in the class might also have, then you can post them on the Q&A on the D2L site.